Hello, everyone. My name is Zach Cole. I am the CEO of Whiteblock. We create tools for peer-to-peer distributed system testing and development. But I am not here to shill Whiteblock today, my friends. I am here to shill our friend the ant. As a model for effective peer-to-peer system design, the ant is a pretty cool dude. Ants work together in a complex, distributed manner in order to perform very complicated tasks as a whole. And the analysis of how these little dudes work together will allow us to create models for more effective, performant, and scalable peer-to-peer systems. So, within an ant colony, when we talk about decentralized control, this is similar to what we assume about peer-to-peer systems and blockchain specifically. Just because there's the presence of a queen does not necessarily mean that she's the one delegating the role of each one of the ants in the network. It's a large-scale system that's self-organizing. Everyone knows their place and they can act accordingly based on simple interactions with each other. The dynamic environment means that they don't have control over their world, just like us, and they're just trying to make do. These are ants. If you'll notice, they have antennae. Look at those antennas. That's how they communicate with one another. When two enemy ants from opposing colonies meet each other, they'll engage in something like a fight. They'll both rub each other's antenna, and they'll posture at one another, similar to how we posture towards one another on Twitter these days, right? And they'll rub each other's antenna, and then they'll coerce each other to feed one another. So they'll spit food into each other's mouths. Interesting point right there. But like I said, just because there's a queen and there are roles of ants within the system does not mean that there's some sort of centralized controller. Every ant inherently understands what its role needs to be within that system. So it's peer-to-peer because these peers are consistently becoming aware of one another. But they may not be aware of the entire global state of the network. One ant doesn't know how many ants there are in the network or what is needed necessarily. All it knows is its most immediate environment and how to react to that immediate environment in order to fulfill its task at hand. So what they do is they communicate via epidemic or gossip protocol, essentially the same way that we communicate messages throughout a peer-to-peer system today. Most of the data is pretty simple. It's just relating to what they know. And that's how it propagates through the colony. One ant sees another ant, it bumps off that information, and so on and so forth. So when two ants are walking along a trail, one ant is going back to the colony to bring the food in, and as they approach one another, they emit pheromones. When they finally bump each other, they touch antenna, and that says, hey, don't go on this path. This trail isn't optimal, or there's better food this way. And that's how consensus is established. So the colony itself works as a singleton. Each ant knows its role without having to be told. And the decision-making is intuitive based on its encounters within its environment. So all of this information propagates back to the queen, who then generates more ants for a particular role based on whatever that need is at the moment. For example, another good analogy for consensus is during like a particularly cold day, ants that leave the colony will gather the warmth of the sunlight. And when they enter that colony again, they'll share that warmth with their friends until they all become green. Let's say green represents the heat. By observing mathematically and boiling that down to some sort of mathematical representation of how this works, we can understand how to more effectively establish consensus within a colony. So the important thing to note is that these nodes are dumb. They don't really know anything. They just use their most immediate environment and the messages that they've received to kind of make these decisions as a whole. And these simple decisions result in complex network actions. So this is like similar to convergence, the idea of convergence. It just means within a finite period of time, we're going to have some sort of transition for the entire network that they're all going to agree upon. But like I said, although the queen she produces additional ants, she doesn't have any control. And there may not only be one queen. There could be certain species have thousands of queens. Or if they don't have thousands of queens, they have thousands of larvae that are lined up to take that queen's place should she fail in her role. So just because there are roles in the system does not mean that it's centralized. It's all about effectiveness and how they can scale effectively and survive as a group. So within a model for peer-to-peer systems, people use, refer to the way that ants work for like the ant colony optimization algorithm or the traveling salesman problem. All of that has been solved by observing how these ants communicate and coordinate amongst one another. What I think would be a good thing to do is observe how these ants perform in order to come up with a more effective light client design and also more effective consensus algorithms. Leader election is another thing that works there. But the way that these ants work together in a way that is largely selfless allows the entire colony to thrive. For example, there are particular types of fungus that can infect an ant, and if a single ant becomes infected, the rest of the colony is going to die. So what do they do to prevent that? They have 2 ants that sit at the door or the entrance to the colony, and they'll smell each one of the ants that comes in. And if they smell that one of these ants is infected, they'll take that ant out to the graveyard, and they'll cut that ant's head off. Then they'll cut each other's heads off. It's kind of weird, right? And it may seem savage, but both of those ants that cut each other's heads off have an understanding that that is their role. And to the foraging ant, he may think that that's savage, but the ants that cut each other's heads off don't know any better, and that was their role in the society, and that's how they survive, because that fungus will take over your brain and kill you. So, that being said, I'm done. My name is Zach Cole. And let's just look at ants, try to figure out how to scale more effectively. Any questions about ants? Anyone? Yeah, so their mandibles have a locking function that's kind of automated. So, you know, like a pit bull has its jaws, you can't open it. So the mandibles will actually force the closure of their jaws when they die. And they do it simultaneously. It's like a cool hug of death. What's that? Yeah, it's an asynchronous process, right? So, yes, Alex Stokes.
Do you have a sense of how big the literature is on like maybe the algorithms people study in these ant colonies? Because like we want to just adapt the same stuff to like our group networks.
Yeah, there's a lot of information. I didn't put it together because I'm not an expert, and I was pretty nervous about this. While I understand a whole lot about peer-to-peer systems, I don't really know a lot about how ants work. So for the past month, I've been doing research on how these ants work so I could show you guys that there's stuff out there that's already done that we can look at in order to figure out how to scale our own network and for our own use cases. In particular, these ants that function as light clients don't have an awareness of the global state, and it's irrelevant to them. But somehow, the entire colony itself becomes aware of exactly what needs to be done in order to scale and survive. How's that possible? Can we reduce these functions to mathematical models? Yes, we can. And people have already done that to like solve stuff like the traveling salesman problem, which can also be observed in like mold colonies. You can see how mold works as a singleton, even though it's not really one particular entity, to find the optimal path to find food. So another example of how consensus works is like when an ant is going to find a pile of sugar to bring back to its colony, how does it know which path is the best? Well, a few different ants need to do that first, right? And then the next ant will observe that that guy came back faster. So he'll follow the pheromone trail to that pile of sugar. The more ants that follow those pheromone trails will indicate which is the optimal path that'll be taken over and over and over again. And that's how they establish it, without any real understanding for what they're doing. You know? So it's pretty interesting.
Do you have any examples of like malicious ants within the colony?
Right, so a malicious ant would be like an ant that is infected with a fungus, right? Well, when we talk about maliciousness within a distributed system, generally people are going to refer to the Byzantine generals problem. They're going to say that's a Byzantine node. A Byzantine node isn't a bad node. It's not a node that's going to like write fuck you on the bathroom wall. It's a node that fails in its process. So that's an example of how ants are fault tolerant. So I would say that the fungal infection itself would be a malicious node because the maliciousness is just killing the rest of the colony. So ants don't intentionally act maliciously, though.
But like, I guess in our network, sometimes we do potentially act maliciously.
Sure.
Different failure case than my node crashed, like I can't keep running. So
Right.
I'm just wondering if there's any time where any like specifically where like fuck you all.
Not that I'm aware of, but if you want to do some research on it, I'd like to learn. So consider this a call to action. Yeah. So just by observing these simple processes in nature, we can really understand how things scale and what can be done more effectively within our own systems. Yeah. Any other questions? All right.